Welcome back to Hypnosphere. You are in a quiet place for slow science, where curiosity is an open window, and every sound is a soft light. Take a breath. Feel the chair, the bed, the couch under you. This is your time to drift through ideas, as gently as clouds crossing an evening sky. Tonight we are listening for something that may or may not exist, and that is part of why it is beautiful. We are listening for a world beyond our world. The question is simple and astonishing at once. Could we ever detect another universe? The word detect is humble. It is not conquer, not prove, not announce. It means noticing. Noticing with care, noticing with tools, noticing with patient doubt. And the phrase another universe is a puzzle box. Do we mean another region of space like ours, too far to ever visit? Do we mean a bubble that formed beside our own in the earliest fraction of a second? Do we mean branches of quantum possibilities that do not meet us again? Our answer depends on which doorway we open, and which kind of testimony we will accept. In everyday life, detection looks like dust glinting at the angle of sunlight, or a faint rhythm you only hear when the room is still. In cosmology, it looks like a pattern in the sky that refuses to be chance, or a curve in data that remembers an ancient event. The universe has left us a baby photo in the cosmic microwave background, a map of the first light unfurling as the hot young cosmos cooled. It has left us the distribution of galaxies across billions of light years, like frost crystals spreading over glass. It has given us faint gravitational murmurs, waves of space-time passing through, and it has offered the smallest differences in temperature and the lightest imprints of polarization. These subtle traces are how we listen. The idea that there could be other universes arrived not like a trumpet, but like a fog. It seeped in as explanations turned into deeper questions. Why is space so uniform in opposite directions? Why is space so flat, as if balanced on a knife edge? Why are the physical constants not wildly different, but rather tuned within narrow ranges that permit the chemistry of life? The theory of cosmic inflation answered some of these questions by proposing that, in its earliest instant, our observable universe expanded faster than light, smoothing irregularities and driving curvature toward flatness. But inflation itself, in many versions, tends to be eternal, blossoming into a garden of bubble universes, each a pocket with its own conditions. In that picture, we live in one bubble, and many others exist beyond our horizon. If that is true, then detecting another universe would not be a matter of traveling there. We would listen for fingerprints of past contact. Two bubbles forming close by in a sea of inflating space could collide. That collision might leave a round scar in the map of the first light. It might seed a ripple in the expansion, a gentle gradient, or a ring of slightly warmer or cooler spots. It might imprint a pattern in the polarization of the cosmic microwave background. Or, if our bubble formed with a specific geometry, the entire cosmos we observe might carry an almost imperceptible curvature that tells us it is a slice of a larger structure. There are other possibilities too, more speculative and maybe forever out of reach. The many worlds interpretation of quantum mechanics speaks of branching realities that do not interact again, at least not in a way we can test. There are ideas about baby universes budding from black holes. There are landscapes of string theory with a near-endless variety of vacuum states, each a different script for physical law. Not all of these visions offer a way to detect a neighbor. Some are like poetry that calms us or unsettles us, but does not guide an experiment. Others point to fragile signals, faint patterns and whispers that could be sought with better and gentler instruments. Wherever you are tonight, perhaps in a city apartment hearing the soft hum of traffic, or in a quiet house where the refrigerator and the night insects make a low chorus, you are sharing a horizon with everyone else listening. If you would like to, you can share in the comments where you are and what time it is for you. Not as a task, but as a small point of light on a map of humans looking up together. We will walk carefully. We will begin with early ideas, with the first pictures of the sky that made the universe feel young and knowable. And we will follow the thread to the edges of what science can say. We will look at signatures that could reveal a neighboring cosmos, and we will accept the possibility that we may never see them. There is quiet in both outcomes. What matters is the way we listen. Settle into your breath. The early universe is waiting for us. The sky keeps its memory in radiation and in space itself, and if we pay attention, some of that memory might be about the neighbors we cannot visit, only hear. Imagine stepping outside at dawn after a light snow, when the world is quiet and the air is still. The ground looks smooth and unbroken. Later, under the sun, tiny ridges and sparkling grains reveal themselves. Cosmology has felt like that. At first, the sky looked uniform in every direction. Then sensitive instruments revealed small patterns that changed everything. The cosmic microwave background is the afterglow of the hot early universe, a bath of light released when the cosmos was about 380,000 years old. Before that, the universe was a fog of plasma, where light scattered constantly from electrons. As it expanded and cooled, electrons joined protons to make neutral hydrogen. Suddenly, light could travel freely. That light has stretched with the expansion of space, and now sits in the microwave band, washing over Earth with gentle uniformity. When scientists first measured it with high precision, it was nearly the same in every direction, a testament to the early smoothing of the cosmos. But it was not perfectly smooth. There were tiny temperature differences of only a few parts in 100,000. These small variations were enough to grow into galaxies and clusters over billions of years. The map of these differences is our earliest deep image of the universe itself. In the 1990s, the COBE satellite confirmed that the microwave background had an almost perfect black body spectrum, the kind of spectrum that comes from a thermal bath. Later, the WMAP mission, and then the Planck satellite mapped the temperature fluctuations across the whole sky with great precision. They also measured polarization patterns, which tell us how light scattered off last-moving electrons, and thus reveal details about the primordial waves and flows. Why do we start here, with this quiet microwave light, when we are asking about other universes? Because if another bubble universe touched ours in its youth, the evidence would most naturally be found in this earliest image. A collision between bubbles would change the density and temperature across a region, leaving a disk-like imprint in the microwave background. Imagine two soap bubbles meeting on a basin of water. The place they touch is a circle. If the collision happened within the part of space that later became our observable universe, that circle could be imprinted on the first light. There are other signals to consider. The geometry of our observable universe might not be perfectly flat. Inflation wants to make space very flat, but a bubble formed by quantum tunneling out of a false vacuum tends to be open inside, meaning it has a small negative curvature, like a saddle surface. If we could measure a tiny negative curvature today, not enough to change our daily life, but enough to put a small drift in the geometry of the sky, it would be a suggestive hint. Not proof, but an arrow. Early researchers also thought about the shape of space itself. What if our universe is finite but wrapped, the way a video game world loops back on itself? Then light could travel around, and we might see pairs of matching circles in the microwave background where the sky repeats. Searches for those matched circles have turned up no convincing evidence so far, but the idea trained our attention to look for large-scale coherence. Astronomers also noticed peculiar features. There is a region in the southern sky called the cold spot, a patch cooler than expected, elongated, and a little enigmatic. Some suggested that it could be the scar of a bubble collision. Others argued it could be a statistical fluke, or the imprint of a massive supervoid along our line of sight that cooled the background slightly as light climbed out of a low-density region. Follow-up studies using galaxy surveys found an extended underdensity, but whether it fully accounts for the cold spot is still discussed. Planck's data mostly favored mundane explanations, but the cold spot remains a friendly reminder that anomalies are the places we learn. While microwave maps matured, the theory of cosmic inflation grew from a clever fix to a broader framework. Inflation explained the horizon problem, the mystery of why distant regions of space have almost the same temperature. If many parts of the early universe were once closer together, inflation smoothing could make them similar. Inflation also explained why the geometry is so close to flat, and it predicted a pattern of nearly scale-invariant fluctuations that matched what WMAP and Planck saw. But many models of inflation do not end everywhere at once. They can be eternal in some regions, with pockets where inflation ends and hot Big Bang conditions begin, while elsewhere space keeps inflating. In that picture, the cosmos becomes a foam of expanding bubbles. Each bubble is effectively a universe. Most pairs of bubbles will be too far apart to interact. A few rare ones may collide early enough that their shock of meeting is inside our past light cone, which is the region from which light has had time to reach us. If so, the first light could recall the meeting. Other branches of multiverse thinking arrived from different roads. Quantum mechanics, taken seriously in the Everett interpretation, says that when a quantum system branches into distinct outcomes, all outcomes exist, but do not interfere further. That kind of multiplicity is not something we can detect with a telescope. Whatever evidence we have for quantum mechanics comes from experiments within our branch, and decoherence hides the others from us by design. So in this tale, we will mostly follow the bubble worlds of eternal inflation, and keep the other flavors in view as philosophy. There is also the landscape idea in string theory, where an enormous number of different vacuum states are possible, each with different low-energy physics. Eternal inflation could populate this landscape, with bubbles sitting in different valleys. That brings us to a quiet and controversial tool, anthropic reasoning. If there is a vast collection of universes with different constants, we should not be surprised to find ourselves in one of the rare universes where those constants permit observers. This is not a detection. It is a way of thinking about why certain parameters lie near the boundaries of habitability. It can feel unsatisfying, but it can also be honest about what we can and cannot compute. Through all of this, the emotional tone stays soft. We ask the sky simple questions, then build instruments sensitive enough to hear whispering answers. The elegance of the early maps gives way to the patience of more refined searches. If another universe left a mark on ours, it is not a message, not a proclamation, but a subtle change in a pattern that only a few thousand people on Earth will ever analyze directly, and that the rest of us will feel through stories like this one. We continue forward toward the details of how such clues could arise, and how we look for them without forcing the sky to say what we want to hear. To imagine how another universe could touch ours, start with a field, a simple mathematical object that fills space with a value at every point, like temperature on a weather map. In many inflationary models, the early universe is dominated by such a field, perched in a high-energy state called a false vacuum. Quantum mechanics allows the field to tunnel to a lower energy state, like a marble slipping through a hill rather than rolling over it. When tunneling happens in one region, a bubble of true vacuum appears and expands at nearly the speed of light. Inside the bubble, inflation ends, and the energy turns into a hot, dense soup that begins the familiar path toward atoms and stars. Now picture an inflating space where bubbles appear here and there. Most are alone. Some are born close enough to collide. The physics of these collisions has been studied in detail with simulations and analytic models. In our observable universe, the effect would be in a azimuthally symmetric disturbance on the sky, a circular or nearly circular feature with a characteristic profile. It would not necessarily be dramatic. Think of a shallow dent on a drumhead that is otherwise tightly stretched. The scale of the circle, its center on the sky, and the amplitude of the temperature change would depend on the timing and orientation of the collision. The collision could also produce a particular pattern in polarization. Polarization in the microwave background arises when light scatters off moving electrons in the presence of quadrupole temperature anisotropies. A collision that introduces a gradient in temperature can generate a ring of E-mode polarization, and in some models, a small B-mode component with a distinctive geometry. The signature would be subtle, because most of the microwave background pattern is a symphony of primordial acoustic waves. Extracting a faint circular whisper from that orchestra is not trivial. Researchers have developed Bayesian frameworks to search for these features. One approach is to model a collision as a disk on the sky with a specific profile, and then compare how well data are explained with and without such a feature. Another is to use needlet transforms, a way of decomposing the sky into localized frequency components to look for circular anomalies. Teams have scanned the WMAP and Planck data for disks over a wide range of sizes and positions. The results so far is that there is no decisive detection. The data slightly prefer models without bubble collisions. That does not mean there were none. It means that if they occurred, their imprints are weaker than our current ability to separate them from the random patterns of inflationary fluctuations. There is a cousin to this idea, less direct, but also telling. If our universe began as a bubble nucleated from a false vacuum, the interior should look like a negatively curved space, an open universe. Inflation inside can reduce that curvature dramatically, but not to absolute zero. Measuring a tiny negative curvature would support the bubble origin story. Current observations from the microwave background, baryon acoustic oscillations in galaxy surveys, and supernova distances constrain the curvature parameter to be within about 1,000th of flatness. Some analyses have hinted at slight deviations, but when all data are combined, the universe looks extremely flat. Future surveys may reach sensitivities of a few 10,000ths. A true detection of small negative curvature would be significant, though still not proof of a multiverse, because other mechanisms could mimic it. But as with faint trails in a forest, consistent marks pointing in one direction strengthen a picture. There are other possible witnesses. Consider the primordial gravitational wave background. Inflation is expected to produce a spectrum of gravitational waves that leave a swirly B-mode pattern in the microwave polarization. Experiments like BICEP Polar Bear, the South Pole Telescope, and Planck have been chasing this signal, constraining the tensor-to-scalar ratio that measures gravitational wave strength. A detection would not directly prove other universes, but it would tell us about the energy scale of inflation. Some bubble collision scenarios become more or less likely depending on that energy. A very high energy inflation could make collisions rare within our observable patch. A lower energy scale might allow more accessible imprints. So gravitational waves act as context. Beyond the microwave background, the distribution of matter could carry signs. A gentle gradient seeded by a collision could affect how galaxies cluster on very large scales. Statistical isotropy, the idea that the universe looks the same in every direction, aside from random fluctuations, can be tested with galaxy maps from surveys like DESI and Euclid. There have been claims of alignments or hemispherical asymmetries in the microwave background on the largest scales, nicknamed the axis of evil, though most cosmologists see these as intriguing but not compelling anomalies. New data will sharpen these tests. Space is like a lake at dawn. Most ripples are from the wind. Now and then, a larger ring suggests a dropped pebble. You look for rings that are too round, too coherent, to be the wind alone. Another window opens at the dawn of structure formation. The 21-centimeter line of hydrogen, emitted when the spin of the electron flips relative to the proton, allows us to map neutral hydrogen across cosmic time. Instruments like HERA and the Future Square Kilometer Array are building three-dimensional pictures of the early universe by tuning to different redshifts. A gentle, large-scale gradient or circular anomaly seeded by a collision might be visible in this 21-centimeter tomography. It would be like seeing the first fog clearing over a lake and noticing that the fog clears slightly earlier along a large circular front. This is a new realm of sensitivity, and it is an invitation to patient optimism. The cosmic microwave background also preserves not just temperature and polarization, but spectral history. If energy was injected into the photon bath in the early universe, the perfect black-body spectrum would be slightly distorted. There are two main types of distortion, called mu and y. Processes at redshifts of millions create mu distortions, while later energy injections create y distortions. A bubble collision that heated or cooled a region early enough could leave a very tiny spectral distortion with a particular angular pattern. Proposed missions like Pixie and Super Pixie have aimed to detect such signatures. These are exquisite measurements, like tasting a single grain of salt in a vast ocean, but they are in principle possible. One can also imagine other relics of collisions, such as cosmic strings or domain walls. These are topological defects that can be produced in symmetry-breaking transitions. If a collision produced a network of strings, they might lens background galaxies, creating distinctive double images, or produce a stochastic gravitational wave background at frequencies accessible to pulsar timing. Arrays and space-based detectors like LISA. Pulsar timing arrays have recently reported evidence for a common spectrum process that may be a gravitational wave background produced by inspiraling supermassive black hole binaries. Exotic sources are not required, but the window is there, and future data will clarify the spectrum and any deviations from the expectation for black holes. If a background with a different shape is seen, it could hint at early universe phenomena. In parallel, theorists wrestle with the measure problem, which is the difficulty of defining probabilities in an eternally inflating cosmos that contains infinitely many regions. How do you say how likely it is to observe certain constants or collision histories when there are infinitely many observers and infinitely many bubbles? Different ways of cutting off the infinities give different answers. This is not a small technical issue. It touches on what predictions mean. For our listening, it means that even if a multiverse exists, some expected signals may be rare. Our bubble could have had no neighbors close enough to collide. Or it could have had many, but the imprints were erased by later dynamics. Patience helps. So does a commitment to data that can turn us around if we are walking the wrong path. At the end of this part, the tapestry looks both rich and delicate. Circular scars in the first light. Slight negative curvature. Gentle hemispherical gradients in 21 centimeter maps. Tiny spectral distortions with a faint pattern. Possible defects and their gravitational waves. Each is a quiet form of testimony. None is guaranteed. The sky is not withholding. It is speaking as softly as it can. We lean in, and in the next step, we will place these ideas beside analogies and reflections that help them settle into the wider picture of nature and our place within it. Picture a pane of cold glass on a winter morning. As the warm air inside meets the chill outside, tiny droplets of water condense. They gather into beads and then into larger circles that meet and leave arcs where they touch. If you could freeze that moment and then look at a small region magnified, you might see a curved line crossing your view, a hint that something met something else just outside the frame. Cosmologists sometimes think of our observable universe like that small region, a window on a much larger condensation where pockets of reality formed and sometimes touched. We see what happens inside our bead. The line is a hypothesis that there was contact. Analogies are imperfect, but they help soften abstract thinking into something you can hold. Consider a lake in a gentle rain. Each raindrop makes a circle of ripples. Most circles expand on their own, overlap, and fade. If you were a small creature living on the surface, and your world was as big as one ripple circle, you might sense your world expanding. If, in the past, another ripple overlapped yours, the pattern inside your circle would carry a slight ring where the waves met. You would not have to see beyond your circle to deduce that an encounter happened. You would only need to map the waves with care and notice the ring is not an accident. In many worlds' quantum mechanics, the analogy changes. There are no droplets side by side. Instead, there is a single expanding ripple where the wave function branches into non-interacting histories. Detection is not a matter of a scar, but a bookkeeping of possibilities that are all real in a mathematical sense. In that picture, talk of detecting another branch is a category error. The branches are real, but causally isolated. The right thing to detect is the correctness of quantum theory itself, which we already do endlessly in laboratories. For bubble universes in eternal inflation, detection is a disciplined version of spotting rings on a lake. Instruments like Planck or the upcoming CMBS-4 and Light BIRD missions are the patient cameras that can see the faintest ripple lines. Galaxy surveys such as DESI, Euclid, and the Roman Space Telescope are like aerial photographs of the lake as it matures, mapping large-scale structure with precision that approaches the natural limits of cosmic variance. The square-kilometer array will listen to the hydrogen fog at cosmic dawn. Together, these facilities make a symphony of listening at different times and in different ways. Beyond observable imprints, there is the more philosophical route, where we ask whether the distribution of constants we measure suggests selection from a broad ensemble. The cosmological constant, responsible for the accelerated expansion of the universe, is small compared to natural scales in particle physics. If it were much larger and positive, structures like galaxies would be torn apart before they form. If it were significantly negative, the universe would recollapse quickly. In a landscape of many possible constants, most universes would be sterile. We find ourselves in one of the few with a narrow window that permits long-lived structures. This is compatible with anthropic reasoning. It is not a proof that other universes exist, but it connects our measured constants to the idea of an ensemble. This way of thinking has its own shadows. The measure problem returns, and with it, the discomfort that comes from arguments that seem to explain everything and therefore nothing. The antidote is to keep multiple lines of evidence in view, with different failure modes, the way engineers build redundancy into spacecraft. Geometric curvature is a different kind of clue than a bubble collision scar. A spectral distortion is a different kind of clue than a large-scale galaxy gradient. If several lines point in a direction, confidence grows. If they disagree, we learn. Black holes invite another analogy. Some theorists have proposed that black hole interiors might seed baby universes. That gravitational collapse, could pinch off into a new expanding spacetime. In such scenarios, universes that produce many black holes have many offspring, and there could be a form of cosmological natural selection or constant drift toward values that favor black hole formation. This is an evocative idea. It leads to tentative predictions, like constraints on the maximum mass of neutron stars. As observations accumulate, such predictions are refined or ruled out. So far, black hole genesis remains an intriguing story without firm observational support. It is a healthy part of science to explore ideas that might fail. Sometimes people ask whether wormholes could let us peek at another universe. In general relativity, wormhole solutions exist as mathematical possibilities, but maintaining a traversable wormhole seems to require exotic matter with negative energy density in ways that challenge known physics. Connections between entanglement and spacetime geometry, captured in the slogan A=EPR, suggest profound links between quantum information and gravity. They may reshape our understanding of spacetime itself. Whether they offer a handle on other universes is unknown. This is where we sit on the shore and watch distant lightning, beautiful but far away. There is a humility built into the speed of light. It sets a horizon for what we can see. There is a humility, too, in cosmic variance. On the largest scales, there are only so many independent patches of sky to average over. You can always encounter a pattern that looks strange simply because you had one realization of a random process. Our methods must embrace humility, not as resignation, but as realism. The joy is in what remains. We can measure polarization at the microkelvin level over the entire sky. We can map the positions of millions of galaxies and weigh their shadows in the distortions of spacetime, called weak lensing. We can hear gravitational waves passing through the Milky Way by watching the steady ticks of pulsars. This is enough to keep wonder close for a lifetime. If the needed signals are very small, a future detection will likely sound like this. A collaboration releases a careful analysis showing that adding a circular template to the sky slightly improves the fit to the data, with a false detection probability below 1 in 10,000. Independent teams confirm it with different methods, different masks, and different assumptions about foregrounds. Over years, polarization data strengthens the case. A 21-centimeter analysis finds a consistent ring at the same location and angular size at high redshift. The measured curvature is small, but negative and consistent with an origin in a bubble. No single piece is decisive, but together they fit like the edges of a jigsaw. The picture emerging is of a neighbor we cannot see directly, only by the way our own sky remembers being touched. And if the detection never comes, that is not a failure. It would teach us that either we had no such collisions in our past light cone, or that inflation took a form that hid them beyond our reach, or that the ensemble is not there in the way we imagined. Non-detections refine theory space. They turn prolific imaginations into smaller, sturdier shapes. The reflection here is gentle. Nature does not owe us spectacle. It offers comprehensibility in pieces we can hold. Our place in the universe is special because this has become our work. To notice the faintest patterns with care and to stand on the planet we grew from, looking back at the moment when atoms were first allowed to become light. Return for a moment to your own horizon. The boundary of what you can immediately sense depends on the light in the room and the sounds that carry in the air. You are inside a small world with edges. Beyond them, other rooms, other lives, continue in parallel. You do not need to see them to know they exist. You trace their presence in the soft thump through a wall, in a light under a door. The cosmos is like that on a grander scale. Beyond the part we can see, something goes on. Whether that something is more of the same, or other universes with different scripts, is a profound question. Our tools may one day find the soft thump, the shallow ring, the faint curve that says there was a neighbor. What might that day look like? It will be quiet. The news will not be fireworks. It will be a graph where two lines diverge and an annotation that says, here is the best fit with a collision template, and here is the best fit without. It will be a polarization map with a circle that remains when several teams remove the galaxy's dust in different ways. It will be a 21-centimeter slice of the early universe, with a disk of slightly earlier heating. It will be a small but stubborn negative curvature, measured by independent probes. It will be a spectral distortion at the level of parts per billion, consistent in frequency and on the sky. It will be a collection of consistent small truths. Someone will open a bottle of something. Someone will cry alone at a desk. Many will argue, and this will be healthy. Confirmation will take time. Doubt is not the opposite of hope. It is how hope learns to stand. In the meantime, we continue to build instruments with tender hands. Light BRD will look for primordial B modes with a gentle focus from space. CMBS-4 will cover the ground with a dense lattice of detectors in the coldest places on Earth. The Roman Space Telescope will chart galaxies and the weak lensing field with stable vision. DESI will continue to sharpen the ruler of baryon acoustic oscillations. The square kilometer array will open the early universe as if pulling back a curtain. LISA will listen for the long waves in space-time launched by supermassive black holes and perhaps by the first transitions in the universe. Pulsar timing arrays will keep refining their hearing of the nanohertz sky. Each of these projects is a form of love, a careful attention made physical. There are also limits we carry alongside our ambition. Cosmic variance says that on the largest scales, we only have one sky. Some questions may be undecidable with arbitrarily high confidence because there are not enough independent modes to average out the cosmic dice. But even then, we can ask different questions. If we cannot see a collision scar, we can still learn how inflation happened, which potential energy landscape the early field moved through, and whether the energy scale allows or forbids particular multiverse scenarios. We can test the isotropy of the universe across as many scales and tracers as we can gather, from galaxies to the integrated Sachs-Wolf effect to 21-centimeter maps and beyond. Negative results are a kind of gentle boundary that shapes better theory. There is a soft philosophy that comes with this. The multiverse, if it exists in any form, does not have to be an answer machine. It can be a background, a context that reminds us that our observed constants need not be the only way physics can be. It can be a prompt to humility that does not dampen curiosity. We can keep attention on the things we can weigh and map and hear, and let the larger picture be a possibility we court with respect. This brings us back to the question we began with. Could we ever detect another universe? Yes, in principle, if our universe bears a specific kind of scar from an ancient meeting, or if its geometry carries the slight bend expected from a bubble interior, or if the first gases carry a circular whisper from a passing wave. We might also never find such signs, and that would be an answer too. In both cases, the practice is the same. We listen, we sharpen, we share our findings carefully, and we welcome the thought that reality might be more layered than our window shows. For you, lying back now or walking or washing a dish by the sink, the connection is not abstract. This question asks something about how we live with the unknown. We can want with all our hearts to see beyond the horizon, and still be at peace with the fact that the horizon moves very slowly. We can be content to know that the universe is friendly to our understanding, and that it sometimes withholds a piece not to tease us, but because the piece is simply too far away. The path is the point. The care we bring to noticing is already a kind of answer. If you feel like it, notice your breath again. In, out. Think of the sky as a room with a light under a door. Whatever is on the other side may remain a rumor for us, or it may, one day, leave a fingerprint on our wall that we can trace with our hands. Either way, we are here together in the dark with our instruments, making the dark a little more intelligible. That is a tender and human work. Thank you for spending this time in Hypnosphere. If this gentle journey brought you calm or curiosity, you are welcome to subscribe. New stories arrive like quiet constellations, meant to meet you where you are and carry you a little farther into the soft edges of the universe.